Okay, so look at the table in front of you, or, the chair you're sitting on right now. It looks solid.
Yeah.
It feels solid. If you hit it, your hand hurts. But what if I told you that solidity is basically a lie?
That's a compelling way to start. And it's not just that it's a lie, it's that the rules holding that table together are so strange they might as well be alien.
That is the premise we are working with today. We're doing a deep dive into the main riddle of the universe based on some really mind-bending conversations with physicist Alexei Semikhatov.
Mm-hmm.
We're talking everything from the quantum world to black holes and why, according to him, our common sense is actually our biggest enemy when it comes to understanding reality.
Right. And Semikatov's main argument here is just fascinating. He says we are these macroscopic giants, these big, clumsy biological machines, trying to understand a microscopic world that is, and this is his word, hostile.
See, that word really stuck out to me. Hostile. It feels a bit aggressive for physics.
Wait.
Why does he call atoms hostile? Is he like anthropomorphizing them?
Not in the sense that they want to hurt us, no. He means hostile to our intuition.
Yeah.
The atomic world is completely devoid of the things that make sense to humans. I mean, there's no shape, there is no smell, there is no color. It is a reality that just refuses to play by the rules we evolved to understand.
So it's a world where our logic just doesn't apply?
Exactly. And yet, if those alien laws stopped working for a single nanosecond, you, me, and that table would just vanish. We are held together by a scaffolding we can't see and can barely comprehend.
So let's try and look at that scaffolding. Semikhatov uses this analogy of a sealed box to describe how physicists study this stuff.
Right.
He says we can never open the box, we can only shake it and watch the dials on the outside.
It's a great analogy because it highlights a hard limit. It's not just that our microscopes aren't good enough yet, it's that we literally cannot see an atom.
It's impossible.
It is physically impossible.
Okay, walk me through that, because I remember seeing pictures of atoms in textbooks, the little solar system looking things. Are you saying those are fake?
They're models, they're illustrations. But you can't take a photo of an atom in the way you take a photo of a face. Think about how sight works.
Okay.
You see something because light waves bounce off it and hit your eye.
Right.
But an atom is about 2,000 times smaller than the wavelength of visible light.
Okay, so the light wave is just too big.
Way too big. Imagine you're standing on a beach and you toss a tiny pebble into the ocean. Does the giant rolling wave change shape because of that pebble?
No, of course not. It just rolls right over it.
Exactly. The light wave just rolls over the atom without being disturbed, so we can't see it.
Yeah.
And because we can't see it, we have to accept something that sounds, well, crazy.
What's that?
Atoms don't have a surface.
This is the part I really struggled with. I get the size issue, but everything has a surface. If I shrink down, eventually I hit the edge of the thing, right?
In our world, yes. In the quantum world, no. And that solar system picture you mentioned, that is the lie of the high school textbook. There are no little balls. There's no hard shell you can touch. As you zoom in, matter loses its thingness. It loses texture. It loses boundaries. It just dissolves into abstract entities governed by pure mathematics.
That's weirdly unsettling. It's
Yeah.
like the closer you look at reality, the less real it gets.
It is unsettling, but here's the kicker. We might not be able to see the machine inside the box, but we know exactly how to operate it. Semikhatov points out that our entire modern civilization is built on trusting these alien laws.
You mean like technology?
I mean the phone in your pocket. That is a quantum mechanics machine.
Right.
The semiconductors, the chips, they only work because we figured out how electrons behave in that weird surfaceless world. Lasers, MRI machines, even basic chemistry.
Chemistry. I usually think of that as, mixing liquids in beakers, not quantum physics.
But think about it at the micro level. When you take a medicine, how does it know to bind to a specific cell in your body? That's a quantum calculation. It's literally the Schrödinger equation playing out in biology. We can't see the atom's surface, but we can predict its behavior with terrifying accuracy.
So we're like wizards using a spell book written in a language we don't really speak.
In a way, yes. And that spell book explains things that classical physics, the physics of our everyday world, says should be completely impossible.
Like the sun.
Like the sun, for example.
Okay, let's talk about the sun. Because apparently, by all logical rights, it shouldn't even be shining.
It really, really shouldn't. The sun works by fusing hydrogen into helium. It takes protons and smashes them together. But what do we know about protons?
That are positively charged.
Right, and like charges repel. So inside the sun, you have these protons rushing at each other, but the closer they get, the harder they push apart.
It's like a wall.
It's like trying to force two north magnets together, but a billion times stronger. It's a wall of repulsion.
And classically, they shouldn't be able to break through that.
Not at the temperatures inside the sun. They just aren't moving fast enough. They should just bounce off. If the universe followed common sense rules, the sun would never ignite.
They'd be a cold ball of gas.
Exactly.
But I'm looking out the window and it's definitely ignited. So how are they cheating?
They cheat by walking through walls. It's a phenomenon called quantum tunneling.
Okay, define that. Is it like teleportation?
Sort of. Remember, in the quantum world, a particle isn't a hard object at a specific point. It's more of a probability cloud.
Right.
It's mostly here, but there is a tiny, tiny chance it's over there.
So there's a non-zero chance the proton is suddenly on the other side of that repulsion wall.
Exactly. It doesn't break the wall. It just tunnels through it. But here is the profound insight that Semikotov brings up, and this is why we are alive.
Why?
This tunneling. It's incredibly rare. The probability is minuscule.
Wait, wouldn't we want it to be common? I mean, we want the sun to shine, don't we? If it's rare, wouldn't the sun be dim?
But think about it. If protons were good at tunneling, if it was easy to walk through that wall, the sun would fuse all of its hydrogen in a split second.
Oh.
It wouldn't shine. It would explode like a galactic bomb.
Wow.
Because the probability is so low, the sun burns slowly. It rations its fuel over billions of years. And that slow burn is the only reason life on Earth had time to evolve.
That is wild. We exist because protons are bad at their job.
We are the beneficiaries of a quantum inefficiency.
But we humans aren't so patient, are we? Semikotov connects this to the hydrogen bomb.
Right. A hydrogen bomb is us saying we can't wait billions of years. We want that fusion energy now, so we have to force the tunneling. We have to heat the hydrogen to temperatures 100 times hotter than the center of the sun.
And the only way we can generate that kind of heat
is to set off a regular atomic bomb first. That's the trigger. We light a nuclear match just to get the protons to overcome that repulsion wall instantly.
It's terrifying, but you have to respect the physics. Okay, so we have particles walking through walls. Yeah. But there is one wall we apparently cannot walk through no matter how hard we try.
The speed of light.
This is where the sci-fi dream hits the Einstein reality.
It really is.
Semikotov is pretty blunt about this. He says warp drives going faster than light. Forget about it. But why? If I have a spaceship and I just keep adding more engines, why can't I just keep going faster?
Because it's not an engineering problem. It's an energy cost problem.
Yeah.
As you get closer to the speed of light, the rules change. The energy you need to accelerate doesn't go up in a straight line. It goes hyperbolic.
Give me a sense of scale here, because I think people hear a lot of energy and think, okay, we just need a bigger battery.
No, it's not a bigger battery. To push a single object with mass, even a tiny spaceship, to the actual speed of light, you would need more energy than exists in the entire observable universe.
All the energy in there.
All of it. And it still wouldn't be enough. It is a fundamental asymptote.
We actually test this, don't we? At the Large Hadron Collider in Geneva.
We do. That's the 27-kilometer ring underground. They spin protons around that ring 11,000 times per second.
11,000 louds a second. My brain can't even process that.
It's 0.999999% of the speed of light. And they keep adding nines to the decimal point. But every time they want to add another 9, the energy bill just skyrockets.
Right.
They're pumping city-sized amounts of electricity just to get that tiny fraction faster.
And what's the point? Semikatov had this funny line about how it's not like crashing Ferraris.
Right. If you crash 2 Ferraris, you get broken glass and a steering wheel. You get debris that was already there. But when you crash protons at that speed, you don't get proton parts. You get new stuff.
Because E equals mc squared.
Yeah.
Energy equals mass.
Precisely. The energy of the collision is so high that it condenses into matter. It creates particles that didn't exist a moment before, like the Higgs boson. We are literally creating matter out of pure kinetic energy.
Now, I have to ask the question everyone asks about the LHC. Are we going to accidentally create a black hole and swallow the Earth?
Semikatov shuts this down immediately. No, it was a viral rumor. The math says no, and even if a microscopic black hole formed, it would evaporate instantly due to Hawking radiation.
Okay, good.
You're safe.
Good, because I have plans for the weekend. But speaking of massive amounts of gravity, let's pivot to the black hole itself, because this is where our understanding of time just falls apart.
It really does. And we don't even need a black hole to see time acting weird. You know the movie Interstellar?
Of course. 1 hour here is 7 years back on Earth.
That's real. It's called gravitational time dilation. Time is not a constant drumbeat for everyone. It flows differently depending on gravity and speed.
But that feels like something that only matters in deep space or in a Christopher Nolan movie.
Actually, it matters on your commute to work, your GPS,
My Google Maps.
your Google Maps. The satellites are high up where gravity is weaker and they're moving really fast. Their clocks literally tick at a different speed than the clock on your phone.
And if we ignored that, if we just assumed time was the same everywhere,
If engineers didn't program Einstein's equations into the GPS satellites to correct for it, your navigation would drift by hundreds of meters every single day.
so Google Maps works because we understand general relativity.
Yes.
That's incredible. But let's take it to the limit. The black hole.
Uh-huh.
Semikov describes 2 realities here that I found really haunting. There's the person falling in and the person watching.
This is the most mind-bending part of it all. Let's say you jump into a black hole. You fall past the event horizon, the point of no return. For you, nothing special happens right away.
Really?
You check your watch, it's ticking normally. You fall until you get crushed by the gravity.
Okay, so I have a bad day, but my time feels normal. What do you see watching from the spaceship safely outside?
I see something completely different. As you get closer to the horizon, the light coming from you, it has to struggle to climb out of that gravity well.
Okay.
It loses energy.
Yeah.
I see you slow down.
Slow down like a movie in slow motion.
Exactly. You start moving in slow motion. Then you turn redder and dimmer.
Yeah.
And then, right at the edge, you stop.
Heads up.
To me, you never cross the horizon. You just freeze there, a fading ghost image, stuck on the edge of the abyss forever.
That is ghostly. So in one reality, I'm dead, and in the other, I'm frozen forever.
Relativity says both are true from their respective reference frames. And it gets darker. Semikatov says that inside the black hole at the singularity, time doesn't just get weird, it ends.
What does time ends actually mean? I can process space ending like a wall. but time.
It means the future ceases to exist. It's a dead end for the dimension of time itself. The math just,
Right.
it breaks. It's a concept our brains are not wired to handle.
Okay, let's pivot before I have an existential crisis.
Mm.
Let's talk about something that sounds hopeful. Teleportation, Star Trek beaming. Can we do it?
Semikotov says yes, quantum teleportation is real, but don't cancel your flight tickets yet.
There's a catch.
A very big one. We can teleport the state of a particle like an electron. We use entanglement to make an electron over here identical to an electron over there. But we aren't moving the matter,
You're moving the information.
just the information. And what happens to the original?
Okay.
It has to be destroyed. You can't clone, you can only transfer. So if we teleported you
The me here in the studio dies.
instantly, and a new you is assembled on Mars. But the real problem is the data. To teleport a state, you have to send instructions.
Semikotov mentioned 2 bits per electron. That sounds small.
For one electron, it's tiny. But do you have any idea how many electrons are in the human body?
A lot.
A number with so many zeros that if you tried to write down the data required to teleport a human, it would exceed the storage capacity of the entire universe.
Wow.
We simply cannot transmit that much information.
So the transporter is out. We're too big. What about quantum computers? Everyone is hyping them as the next big thing. Are they just super fast supercomputers?
That's the common misconception. They aren't just faster in terms of clock speed, they think differently. A normal computer is like a mouse running a maze. It tries left, hits a wall, goes back, tries right.
One thing at a time.
One thing at a time. A quantum computer is like pouring water into the maze. It explores all paths simultaneously. It uses probability to cancel out the wrong answers and amplify the right one.
So it kind of feels the shape of the answer.
Exactly. But the problem is fragility. These things are incredibly sensitive to noise, heat, stray magnetic fields. They crash constantly. We're in a race to see if we can make them stable enough to actually be useful.
Speaking of useful, let's wrap up with something concrete. Space travel. We've got Elon Musk trying to get us to Mars. Semikotov had a pretty sober take on this, didn't he?
He did. He basically threw cold water on the idea of interstellar travel leaving our solar system. He says the rocket equation is a brutal tyrant.
This is the fuel problem.
Right. To go fast, you need fuel. But fuel has mass. So you need more fuel just to push the fuel you're already carrying. It's a vicious cycle. We simply cannot carry enough chemical fuel to get to the stars.
It's impossible.
Physically impossible.
So no Star Wars. But he was surprisingly positive about what Musk is doing right now.
He gave Musk credit where it's due. He said Musk isn't inventing new physics. He's changing the economics.
The DHL comparison, I love that.
It's the perfect analogy.
Yeah.
Before SpaceX, a rocket launch was like building a custom Ferrari, driving it once, and then crashing it into the ocean.
Insanely expensive.
Musk is turning rockets into delivery trucks. You drive it, you park it, you refuel it, you go again. It drops the cost of putting a kilogram into orbit by a factor of 100, maybe even 1,000.
Right.
That is how you build a space economy.
Not with warp drives, but with logistics.
Exactly.
So pulling this all together, we've talked about atoms we can't see, a sun that burns on a glitch, time that stops, and space travel that's limited by the weight of gas. It feels like we were surrounded by walls.
I think Semikotov sees it differently. He sees those walls not as prisons, but as the rules of the game. I mean, look at what we've done. We can't see the atom, but we built the smartphone. We can't break the light speed barrier, but we can look back to the beginning of time.
We've learned to surf the alien laws.
Exactly. And Semikotov leaves us with one final piece of advice for the future. He says the most valuable skill for the next decade is to think algorithmically.
What does he mean by that?
He means Understanding that the world, whether it's physics or AI or the economy, is a set of inputs and outputs. It's about shaking the box. Don't just stare at the mystery, figure out the algorithm inside.
That's a great takeaway. The universe is a black box, and our job is to figure out the code.
Precisely.
Well, consider my brain sufficiently broken and rebuilt. Thanks for guiding us through the quantum weirdness.
My pleasure.
And to you listening, keep shaking that box. We'll catch you on the next deep dive.